It's live.
All right, we're live.
And I'll click here.
Okay, so this first question, a bit of definition first. An increasing function is just defined as one which where f of x keeps going up as x goes up. There's no like where sine functions, things going oscillating, no going down. It's always increasing. So how do we show this? The way you tell what direction a function is moving in is you use the derivative, the first derivative. This gives you the slope. So obviously, if the slope is positive, the function is increasing, and so on. Now, if you want to show that it's an increasing function, you've got to show that it increases for all x. All x element of the real numbers. So in something like pure 1, you won't have to worry about anything other than the real numbers. You don't have to really worry about complex numbers or anything else. But this is just to show you that's clear, because maybe this function could have some different behavior if you allowed complex values of x. So the way we define an increasing function is if of x dx is greater than or equal to 0 for all x in the reals condition you have to fulfill. So all you have to do is differentiate this. It uses some application of the chain rule because it's a function of a function. It's a cube of a polynomial. But that's just a very straightforward application. You can crunch through it and get the result, and you'll find something that is always positive or equal to 0. For example, if you end up with something that's squared, you know that because x is a real number squared is always positive. Squared can be negative. That's why they're clarifying it there. To start you off. Okay, so the next question focuses on expansion. So an expansion is a way of approximating a function when you around a certain value. So a Taylor expansion can actually be a good approximation of the behavior of a function. You pick the point. Usually, and sort of implicitly with these questions, you're looking at around 0. Something which is some expansion. Okay.
Is it not on? Interesting. Our first challenge. You know what I might do? I might take some of these guys out.
I can keep talking.
Yeah.
So an expansion will be like a series. So a Taylor expansion is a polynomial in x. So you'll have a term with no x involved, x to the 0, a term with x, which is x to the 1, a term with x squared, x cubed, so on and so on. As you add, the more accurate the expansion is. That's the whole point of an expansion. A Taylor expansion around 0 is often called a Maclaurin expansion, but that's what they mean here. And they're asking you to find the first 3 terms. So this is simply a formula, and it'll be in the formula booklet. You basically apply the formula, but the thinking behind it is that you're trying to model the behavior of the function with a polynomial series rather than, just what does that something raised to 6 look like? It doesn't really give you an intuition.
Don't worry, that's what we're testing it. I can't get it to work just yet. Rub out. Yes, that's brilliant. For some reason, this isn't.
Try again.
It's just okay. So I'm going
Look
to
at the size. Maybe the size has gone to 0 or something.
It's possible.
1 point.
That's okay. We'll try it. I think it might be an error on this. I'm going to try saving it and then opening it up again.
Okay. So if you actually graph what the expansion looks like as you add each term, the first term will just be a number. It'll be like your first terrible approximation of the function is f of x is equal to 5, for example. Well, that's just going to give you a line at x equals to 5. It's probably not going to be a good expansion of this 6th order power function. The next term you add will be a linear one. So you'll have a sort of y equals mx plus c thing.
Hang on, we are back on, but I want to just check because I might do the screen share again. Yeah, thought because the application went. Try that.
Okay.
Try that.
So
I think I changed the size, so it's quite too. You want to make it smaller. Yep.
Okay, so f of x, and we use these to say about equal because only an infinite expansion will actually be a perfect approximation. It's about equal to say a naught, so some constant, plus a1 x plus a2 x squared plus blah, blah, blah. So the first one, if you graphed it, would give you something like that. The second term might give you a nice sort of slant. The third term would give you a parabola because it's a quadratic function.
Mm-hmm.
A cubic term would give you a cubic function, and so on. And so you might find that, say this was your actual strange, weird function, could be anything. The first term would look like that. The second term might look like that. The third would give you some nice parabola behavior. The fourth might fit a bit better, and so on. At an infinite number of terms, you would exactly approximate the function, but you see that it only approximated around 0, so that's the point.
So that what you've written there on the left, the a0 plus a1, those are the different, yeah.
So if these are
shapes,
coefficients, so what they want here is basically to find the coefficients that are in front of these first three terms: the constant coefficient, the linear, the quadratic, the cubic, and then we just say fourth power, fifth power term. So this is very useful in physics if you guys are planning to take physics when you only are interested at very small values of x, so you only care about approximating it around 0. The next one is exactly the same, just applying the formula, except now, I didn't clarify, the formula involves derivative. So to get this term, you need the first derivative of the function. To get this term, you need the second, and so on. And that is in the formula booklet. This is asking you to do it again, and it's just that the differentiation is slightly more tricky. You need to use the chain rule and the product rule. And you'll be able to expand that. But it's very mechanical. You just crunch through it, plug it in, and you get it. Okay, so the next question, this is some actually fairly straightforward geometry once you've interpreted it. It all kind of relies on recognizing that if you have this segment of a circle, the ratio of the volume of that segment to the volume of the full circle is the same as the ratio of the angle subtended, which is that alpha, that's what subtended means. It means like if you have a slice, what is the angle of the point of the slice? The ratio of that angle to the total number of radians or degrees or whatever you're working on. So here, we know that the angle is alpha, and so we have the ratio of, let's call this volume area. This area 1, and so the ratio of area 1 I don't know why I wrote it like that. Area 1 over the area of the full circle that this slice forms a segment of. So not this little small circle, but the full one. You know, going up there, all the way around here, blah, 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 blah. Anyway, it's got a radius of 8 centimeters. So it's this mega one. It's twice the radius of the bottom one. So the ratio between the area of this slice and the area of, let's call it the big circle, or rather circle with radius 8, it's more clear, is the same as the ratio of the angle to the number of radians in the full circle. There's always 2 pi radians. If you haven't worked with radians before, it's It's just another way. It has some very convenient properties that you might encounter later on. But essentially, you could if alpha was given in degrees, you could just divide this by 360. So now we know this area of the 8 centimeter radius circle. We have that. That's basic pi r squared. We know that A1 is half of the area of this semicircle. So what's the area of this semicircle? Well, it's the one with the radius 4, and it's half of the circle. So we say it's 1/2 pi 4 squared. And we know that A8 is equal to a half of that. So that's 1/4 pi 4 squared. So we have this. Whoops. We have A8, no problem. That was just the radius of the big circle. I'm sorry, that should be A1.
Yeah,
That's the slice. We have A1. We know what 2 pi is. We solve for alpha. It's going to be in terms of pi because who wants to deal with loads of decimal points? But that's all there is to it. And the perimeter, no big deal. You just have to know, again, this ratio, this alpha over 2 pi ratio also applies to the section of the perimeter as a fraction of the full circumference of the circle. It's exactly the same. It is alpha over 2 pi. So we say the perimeter, let's call this B. Why would I do that? That's the name of it. P of the slice. P slice is going to be equal to alpha over 2 pi times the circumference of the big circle. And that's the key point of this whole thing is that the alpha gives you this ratio, and that applies to both the area and the perimeter, and the rest is fairly straightforward.
Mm-hmm.
Okay, this next question is just requires you to think about what a geometric progression is. So by definition, it's one in which it's a series of terms, and one in which each subsequent term is some constant ratio of the previous one. So we can again express this as a series, so say A0 is our very first number, plus A1 times R, plus, A1, A0 times R. So you start out with one particular number, A0, and then each subsequent thing is just multiplied by some number, again and again. So you know that if I take this term and divide it by the previous term, I get R. If I take the third term, I also get the same ratio. So each subsequent term will, if I divide it by the previous term, will give me this constant ratio R. Okay, I'm not sure what's going on.
I'm not sure what's going on.
I
think it's just taking a second to update, isn't it?
Maybe. Okay, so we're given 2 of the terms. So we know that the third term, which is this one, and the one thing you should avoid getting mixed up with is the third term is actually the R squared term. The R cubed term is the fourth term and so on, because we've got this initial x to the 0, R to the 0 kind of term. So we know that this is minus 108, and we know that A0 R to the 5th, the 6th term, is 32. So from that information, we can work out R.
Should maybe just do that bit just to show that
Sure.
in the layout.
Okay, so we have that A0 R squared is equal to minus 108, and A0 R to the 5th is equal to 32. So if I now divide this term by that term, well, the A0s will cancel, This will cancel 2 of those, so I'll get r cubed is equal to 32 over minus 108. And then this is just a calculated thing. You take a cube root, and actually what you get is minus 2/3. And that sort of makes sense because you've got a series which is where the absolute value of the number is getting smaller, but it's also switching from minus to plus, so it makes sense that the ratio wouldn't be some big positive number because it would just grow to infinity. So from this, we can again just solve for the first term. So say we take, again, what do we know? We know that a0 r squared is equal to 108. We know r now. We know 108. We just go a0 is equal to minus 108 over 2/3 squared. And that's it. The sum to infinity, once you've got a0 and r, you can calculate the sum to infinity. It's just a formula. It's in the formula book. You can look at a different derivation if you like, but I wouldn't worry too much about it. Mm-hmm. They won't ask you to actually talk about where that comes from. Okay. Any questions so far? No? All good? Okay, so this is a trig question, as you can see. All of the trig identities are in the formula booklet. It's exhaustive, so you don't have to worry about memorizing any of these. This one is just literally pulling these two, getting a common factor, which is going to be these two multiplied together, which gives you exactly that.
You can see that. So what's the trick? What should they look for on something like this? Yeah.
This one, the only trig identity you need to use is that, I'm just going to use S and C as a shorthand, is that S squared plus cosine squared, if they're of the same angle, so I should say theta, sine squared theta plus cosine squared theta is equal to 1. And that, in fact, both of these pretty much only require that identity. So in this one, you just pull it together like you would with any fraction, find the common denominator, sort of. So you get sine of theta. So the common denominator now is sine theta plus cosine theta, sine theta minus cosine theta. This one gets a sine theta minus cosine theta, plus cosine theta times sine theta plus cosine theta. The thing on the bottom, because it's one of those where it's like x plus y, x minus y, the middle term disappears if you just multiply it out to get a quadratic, and you end up with sine squared theta minus cosine squared theta. On the top, this is going to give you a sine squared. This is going to give you a minus sine cosine. This is going to give you a plus sine cosine. And this is going to give you a cosine squared. So you find the mixed terms disappear, and you're left with sine squared plus cosine squared, which the identity tells us is 1. And there, you've solved it. So in the second part, they're asking you to apply this. They've given you that this whole business is equal to 3. So therefore, of course, this whole business is equal to 3. So we solve 1 over sine squared minus cosine squared is equal to 3. So sine squared minus cosine squared is equal to 1/3. So now the trick is to substitute in from our identity. We see that cosine squared is equal to 1 minus sine squared. Plug that in there. We get 2 copies of sine squared minus 1 is equal to 1/3, which gives us that sine squared theta is equal to 1/3 plus 1 is 4/3 divided by 2 is 2/3. Not done yet. Now we have to take the square root. So we must remember that the square root can be positive or negative. So the sine of theta is plus or minus the square root of 2/3. And now, there's more space. Oh, great. So what are we looking for? We're looking for the value of theta for which the sine of theta is plus or minus 2/3. And we're told that the range we're interested in is 0 to 360 degrees. Why is this important? Well, theta is an angle, and so any function of theta is going to repeat itself every 2 pi radians or every 360 degrees. So usually you'll want to sort of, they will always tell you which range you're interested in, but otherwise you have this infinite many answers which would give this answer. So if we look at the graph of the sine function, so here we have theta on the x-axis, and we have sine of theta on the y-axis. Let's say we have 360 degrees there, 180 there, 90 there. The sine function, it's important to know, looks like that. Starts at 0, ends at 0. Its maximum is 1, and its minimum is -1. Cosine is very similar, except it's sort of shifted so that this point, it's shifted by 90 degrees sort of that way, so it starts at 1 and then comes down and ends at 1. So square root of 2/3, I mean, who knows, but it's probably somewhere around there. It's definitely smaller than 1, and it's definitely greater than 0. And here it is again. We're also allowed minus square root of 2/3, so that's over there. And over there. So we see that we have these 4 points, which are values of theta for which, if I plug them into the sine function, I will get the square root plus or minus the square root of 2/3. And that's what I want. So if you plug it into your calculator, using the inverse sine function, which I will just emphasize, can be written like this, but does not equal this. Sine to the -1, or inverse sine, also called arc sine, is the inverse function of sine. This is simply 1 divided by sine. You can think of what goes into inverse function. Well, when I take the sine of theta, I'm plugging in an angle, and I'm getting not an angle, a number, some ratio of the sides of a triangle or something like that. Therefore, my inverse function needs to take in one of these numbers, not an angle, and spit out an angle. This is just 1 over the sine of x. Sine takes in an angle, so this cannot be correct as an inverse function. Arc sine of x is the function you want. So if I plug this into my calculator with square root of 2/3, you take the positive one first, it will give you the first one. So that's called the principal value. So the calculator gives principal value. Now we can work out the other ones ourselves. So the principal value is basically this distance. It gives you that value of theta. Well, this one is simply that distance below the 180 mark. So you have, let's say, theta naught. I can't remember what exactly it was in my calculator. The next one will be 180 degrees minus theta naught. The next one, look, it's just that same distance after 180. So we'll take 180 plus theta naught. And the last one is just that same distance below 360. So we have 360 minus theta naught. And that's all they've asked us for because that's the only range they were interested in. The sine function will keep going on forever and producing, values here, but we're not interested in them. So that's all there is for that question.
Right, let's just have a little break for the guys. We'll leave this on. So just go and freshen up. You should leave the room, but be back ready in about 4 or 5 minutes because you need your brains just to clear for a bit. Okay, excellent. One, go. Quick walk. Cool. So
Bit of a mess.
doesn't matter about that. We're working it out. We're just seeing what happens. Now he's probably asking for the online waiting to join the masterclass. So what I need to do is I need to, yeah, I should have done that beforehand, but I couldn't work out. Is that it?
There you go.
That's it.
Can they, well, while it's live, go back and watch the thing?
Yeah, not while it's live, but they can watch it from the beginning afterwards. I think they can join it and they'll watch the whole thing. I'm enjoying this. Going great. I mean, this is, that's, you know, it's not till October till we properly do the real one. So this is just all testing. So you have a little second as well. You can join this live now. And you will be able to watch it or replay it. So, oh! Cool. I mean, I kind of want to keep that because I want to be able to like communicate with people. So, you know, this should be a bit of a back channel, but there's a smarter way to do it, which is through my phone, because then I can ask the questions so it's not coming on the computer. So I'm probably going to quit Slack from here, and that should help speed up as well. Because it was getting a tiny bit sluggish, wasn't it?
Yeah, a little bit.
And also we're sort of testing how it goes. The one thing I thought was nice. I thought it was good. So I don't know. I mean, this is still being recorded, but so
Can't read me out.
yeah, exactly. So let's say, okay. Now what will be nice as well is, okay, it's not bad actually. Maybe Slack. This will be okay. So when you join them, I think recorded. Okay. Now I think undo's faster. Just also because then you won't have to rub out. You know, if you go over something, yeah. But we can save this. And let's save. Brilliant. Okay. And we've got. Well, the thing is, I think you're going the right pace because it gets a bit harder. So I think you'll aim to do. I guess probably as they get harder, you're going to. I mean, tomorrow's a mechanics one, isn't it? No, you're not doing. You're doing Wednesday. Wednesdays.
The one on the sprinters is mechanics.
Maybe I can't remember exactly. I think on Trello. Okay. I think you're going to do Wednesday and Thursday as well, aren't you? Okay, great. So I think that's, I think about, if you look at marks, I think getting through about 5 or 6 questions in the first one is probably okay, and then probably 3 or 4, and then by the end it's like only 2 or 3 questions because they tend to have, if you look at the marks, you know, that's 12 marks. And then if you look at the marks for the first questions, it's only 3, 4, 5, 6, 7, 8.
That's true. 9,
10, 11, 12, 13. So it's only 13 marks for the first 3 questions. So you've done 13, about 25 marks. It's about, because there's 75 marks on a paper.
Yeah.
So about 25 marks. So you've done 4 and 7. That's 20. You've done 26 marks. So you're about bang on.
Great.
Perfect. Okay. Cool. Awesome. I will get them back in. I just need to. And that's working well as well. It's fine. What you could do, you might want to zoom in a little bit to give you a better question.
Yeah.
You might need a little bit of space more, might you?
I think I can use that corner up there.
Yeah.
Maybe.
Yeah. You can. Cool. What we really need is Okay, back in the room. Slightly refreshed, everyone, after a few minutes.
Yes.
So this is a bit we have to get on the video. I'm not sure in the future whether we'll work out, but it's better to do 3 short ones once we get used to it. It may be better.
Do you work out some of the problems with, I don't know, pens and stuff like that?
Yeah, we did just improve slightly. I think it doesn't help that it's using up a lot of power to try and get, I've closed all the other things. In fact, there's one more. I'm just going to close.
Okay.
Or crack on. Okay, so far away.
Right, so vectors, very important and fun topic in maths and physics. Now, I don't know whether you've seen vectors expressed in this form or in other forms before. I always prefer to write them as columns. So let's look at the vectors they've given us. They've given OA. You may see this notation where there's an arrow on top of whatever the vector's name is. You may also see an underline. In printed stuff, it's often written in bold. So in fact, if you look at these guys, that is often how a vector will usually look in printed matter. It will just be a bolded letter. Anyway, but given...
It's hard to show in shorthand, isn't it, if you're writing.
Yeah, if you're writing, don't try and use bold. Use either an arrow on top or an underline. So here we're given OA, which I'm going to write in a column in this form. 1, 2p, and q. So what they're telling me in this format, these things in bold are the basis vectors of our space. So an x, y, and z directionality. So it's telling me that this thing is sort of 1 unit in the x direction, 2p units in the j direction, and q units in the k direction. Those units can be whatever, meters, centimeters, angstrom, it doesn't matter, but just unit. We unit this here, unit as defined in our space. Everything just has to be relatively consistent. So this is a nice shorthand way of writing these things. Know how they work. But for vectors, what does multiplication really mean? Multiplying 2 vectors together. You have to actually define that. What do you get another vector at the end? Do you get a number? There are in fact 2 types of product, things that are called products in vectors. There's the dot product and the cross product. The dot product, also called the scalar product, will give you a number, a scalar, not a vector, not a matrix, nothing fancy, just a number, which is called a scalar. The cross product, also known as the vector product, will produce a vector of the same dimension as the 2 that you're multiplying together. And you can only do it for dimension 3, but you can't do it for 2-dimensional vectors. Anyway, you don't have to worry about the cross product in this section, but you only have to worry about the scalar product, the dot product. So it's in the formula booklet, but if you have this dot product, v dot w, I actually prefer to write underlines for my vectors. that's equal to the first component of V times the first component of W plus second component of V, second component of W plus, and this works for any dimensionality of vectors. It doesn't have to be 3. Could be 2, could even be 1. In that case, it could be very, very simple. Now, this is one definition. It is quite fairly easy to show that it can also be thought of as equal to the magnitude of V times the magnitude of W times the cosine of the angle between them. So this is why we use it when we're talking about things that are perpendicular or parallel. If they are perpendicular, well, if they're parallel, then theta is obviously 0. So cosine of theta is 1. And therefore you get the actual maximum value you can get, because cosine of theta is only, it oscillates between 1 and -1. So if they are completely parallel, that first bit would just be the magnitudes of them multiplied together. This notation, these like bars, we're used to using them for absolute value. When you use them for vectors, it means the magnitude. So if you think of a vector as an arrow, just what's the length of that arrow? And that is the magnitude, it's just a number, without talking about what direction it's going in. Now, if they're perpendicular, that means there's a 90-degree or pi angle between them. Well, then cosine theta, if you think of the cosine function, looks like that. Well, it actually looks like that. This is 180, this is 90, cosine of theta is 0 at 90 degrees. So if they are perpendicular, this is equivalent to saying that the dot product vanishes. So to do this question, you look at OA, you look at OC, you calculate the dot product between them in components, like this, and you find an expression that is just in terms of P and Q, and you'll find that it's equal to 0. Basically, all the terms will cancel out, and you'll find something that's equal to 0 for any P and Q. So it doesn't require P or Q to be 0. In fact, you can't have P and Q being 0. This is just a bit of a subtle fact. But if you had P and Q as 0, then the line OC, the vector OC, would just be the 0 vector. So if P is equal to Q is equal to 0, then OC would be equal to 0, 0, 0, which is the 0, it's also called the 0 vector. And you can't take dot product, I mean, it's trivial, basically, and in that it sort of doesn't count in mathematicians' terms.
2 seconds. We just had Albert saying he can't see the video, so I'm just going to double check that it's aha. Because we're probably on a 4G connection, it might lose it a little bit. So try that again.
Okay. So that's now fairly mechanical for you. Use the formula to calculate the dot product and show that it equals 0 for any P and Q. So the next thing is to find the magnitude of this vector, CA. Now this is not one of the vectors we've been given. The key point to realize here is that vectors are kind of like giving someone direction somewhere. This one is saying if you want to get from the origin to A, you need to go 1 in the x direction, 2p in the y direction, and q in the z direction. I shouldn't say x, y, z, the i, j, k direction. Right. This might not be real space. This might be some fancy physics problem. You could have any number of dimensions in general. So really, it's just direction. So if I, for example, let's think if I had, say you're standing in a field, you're over here, and I tell you how to get to point A. Well, that's just a vector. This is 2-dimensional. That's just a vector like that. It'll have components 1, 5, or something. Then I tell you go back to the origin, and I'm going to tell you how to get to point B. Well, this is another vector. But now say you want to get from point B to point A. but you don't know how to get there directly. Well, first, you know the way from B to the origin, and you know the way from the origin to A. So that is what you do. You go back there, and then you go up this one again. So this first one, if we think of B as a vector, this thing is just going the opposite direction, but in other ways is identical to B, so we call it minus B. It's following B in the opposite direction. All of the components are inverted. And this is just A again. So the vector, it's exactly the same as giving you directions from B to A. This will give you exactly the same vector. Let's call it, vectored V. So V is just equal to minus B plus A. Yeah, okay, following this direction will just take you a lot longer to get there than going to zip over there, but in vector terms, it's completely equivalent. It's just directions from one point to another. So in this case, we're looking at one which takes us from C to A. So we're starting at C. So we know how to get from the origin to A. So CA must be equal to, firstly, going from the origin, going backwards from C to the origin. So it's minus the vector from the origin to C. And then we're now at the origin. We add OA to get to A. So that's easily calculable. With vectors, if you add them together, you just add the components all separately. No problem. I mean, it makes sense, right? Like if I tell you to go north 1 meter and then north another meter, it's 2 meters north. If I tell you then to go, east 5 meters, it doesn't affect how north you've gone. These are all independent directions. So if I add two vectors together, I independently add all the components to produce a new vector. So now we've got our new vector, and it's actually going to be, here we go, 1 plus 0. Oops, yeah, wait, no, I'm looking at the wrong one. Sorry, OC and A. In fact, it's a bit long to write out, but it's going to be, the first one's going to be 4p plus p squared plus q squared plus 1. This one's going to be 2p minus 2p, and this is going to be q minus q plus q. So essentially, the lower two ones are going to cancel out. So you're going to get, basically, you're going to get this vector, 4p squared plus q squared, 0, 0. Very convenient for the cancel out. Now it's asking you for the magnitude. So this is the distance that you've moved in the I component direction. So you haven't moved in any other direction, so the length is just going to be that. The magnitude of the vector is just that. That's why they made it easy for you. Now, this is not, you may often come across questions where it's not so easy. You have to work out the magnitude, even though, there are non-zero components in several of the components. But that's just Pythagoras. If I want, if we remember here, if I have this vector v, which is made up of some, some x, so some v in the x direction and v in the y direction. And remember that I, j, and k are all perpendicular. There's 90 degrees between them. Well, you know how to find the length of this. It's always just going to be the square root of vx squared plus vy squared plus vz squared plus maybe more dimensions in your space. Well, does this look familiar at all? It looks, the thing inside the square root looks a lot like the dot product. But it kind of looks like it's the dot product of something with itself. So instead of being v1, w1, it's just v1, v1, which is just v1 squared, plus v2 squared, plus v3 squared. So the magnitude of a vector is the square root of the vector dotted with itself. I think it's a nice way to think of it. And it's exactly the same law as Pythagoras, just extend it to whatever many arbitrary number of dimensions. Okay, so in this case, it was just simple. You knew that it only had one component, so it was obviously that was going to be the distance it traveled. So in the next sub-question, you're looking for the unit vector parallel to BA. So first you calculate BA using exactly the same way we calculated CA. It's going to be minus OB plus OA. Again, remember, I always think of it as getting from B to A. How do I do that? Using only the sort of paths that I know. You construct it. And remember to go negative if you're following the path backwards. Now, we're thinking of something that's parallel. And the important thing here is to kind of realize that vectors are not just ways to get to points, they're movable. These points are all defined by a vector that goes from the origin to the point. But that vector is just an arrow. It just has it has a magnitude and it has a direction. You have to then specify if it has a starting point. It's points from O to A or whatever, but really you could move that arrow around. So if we're looking for a unit vector parallel to BA, we don't have to worry about where it starts and where it ends. It just has to be in the same direction as BA, but of unit magnitude, which means magnitude 1. So if I have, basically I need a vector which looks like BA, but if I go and take the magnitude, I will get 1. So if I have some arbitrary vector, three-dimensional vector, say ABC. Now, if I take the magnitude of this vector, I get the square root of A squared plus B squared plus C squared, as before. So if I want this thing to have unit length, all I have to do is divide by the magnitude. And this is called normalization, and it's used all the time in physics. When you want a vector that you only really care about the directionality, you don't want any sort of like magnitudes mucking up later operations. So you do what's called normalization, and you make it into a unit vector. So this is often designated by this notation, v hat, which is equal to v, but all divided by this number, which is the magnitude of v. And that is all that means. The unit vector parallel to BA is just BA normalized. It's parallel because it is the same vector. Basically, you just changed the length of it by dividing it by some scalar, some number, which is the magnitude of the original vector. Does anyone have any questions about this section? Yeah?
No? Good. Maybe do one more.
I've got
a question?
Yeah.
Maybe you said that the vector OA minus OC is equal to 4p squared plus q squared.
Yeah.
Isn't it also plus 1?
You're absolutely right. Oops. Yes.
Good spot.
Good spot. That's exactly right.
Where did that one come from, Mark?
The vector OA.
That's it.
Miracle. Yes. But happily, you're going to have to apologize for the other parts because they actually do still count. But yeah.
It's always different when you're writing on a big screen as well. It's easy to miss. Yeah. So brilliant.
Okay.
Good.
Thanks.
Good, and well done for asking when you sort of could have let it go, right?
Yeah.
Okay, so it's important.
It's important because these things get saved when we do, so that kind of persists and is embarrassing forever.
Yeah.
So we can edit it later.
We'll sort it out in post.
Okay.
Okay, so question 7. So this is basically about a parabola in a straight line. So you should recognize that a quadratic equation produces a parabola, and that a linear equation produces a line. That's why it's called linear. And they're asking for you to consider an intersection between these two. So how do you find intersection points? Well, these two equations, they're referring to they're just sort of describing a general x and y. And this is the relationship between x and y that is satisfied by every point that is on the parabola. Any line, curve on the space is just an infinite set of points. And every single point will have 2 coordinates, and those coordinates will obey this equation. Lines, they will not necessarily obey that equation, but maybe some of them do. And those are the ones that lie at the intersection of these 2 curves. So an intersection point, let's take that one. So an intersection point some point, I'm going to say x, y, I'm going to say x naught, y naught, just to emphasize that I'm referring to a specific x and y, where x naught and y naught obey both equations. Okay, so how do we use this fact to find the points? Well, in this case, we'll be looking at this, just this one point, for example. Y naught is equal to x naught minus 4x naught and plus 4, and also that exact same y naught is equal to m x naught. In our first question, m is equal to 1, so they've given us that. So these 2 y naughts, they're the same number, because I've just, I've called them y naught, I'm just referring to a specific number. So I can set both of these equations equal to each other. Now you're going to have a quadratic equation, x squared, I'm going to drop the naught for now, minus 4x plus 4 is equal to x, m being 1. Take that over, you're going to get minus 5 is equal to 0. Well, this is just a quadratic equation, and you can solve it.
They get the formula for that as well in the booklet. So.
Yeah, so this is the formula that is probably going to end up being ingrained on your heart for the rest of your life. Minus b plus or minus the square root of b squared minus 4ac all over 2a, which is sort of known colloquially as the formula, but that is a way to find the roots of any quadratic equation. So in this case, we can actually just factorize it, I think, if you know. But okay, so that one's factorizable. You don't have to worry about the formula. But if you're just staring at it and you can't seem to factorize it, just go straight to the formula. Don't worry too much. It doesn't really waste that much time. So here we see that both the points where x naught is equal to 4 and x naught is equal to 1 are both points. They are the x coordinates of intersection points. You find the y coordinate by just plugging them back into one of the equations. I would recommend picking this one because it's really short and not bothering to solve for y here. But this one gives us y is equal to 4 because y is equal to x in this sub-question, because n is equal to 1. And here, y naught is equal to 1. So we have 2 intersection points. The point 4, 4 and the point 1, 1. So we can picture a line joining these 2 points. And let's think of just, here's 1, 1, and here's 4, 4, and here's A, B. Well, they want the coordinates of the midpoint. Now, visually, you could pretty much see this. If you think of these as being the hypotenuse of some right-angled triangle, it's pretty simple to see that the halfway point will split this distance and this distance in its coordinates, right? So they want these coordinates. So we know that over here is the coordinate 1, oops, and over here is the coordinate 4, x. And on y, this again is 1, blah, 4. So this distance between them is 3. If this thing sort of goes half the distance, it goes 1.5 on from 1, giving you 2.5. So this is going to be the point 2.5, and this is also going to be 2.5, and those are the coordinates of the midpoint, and that's all there is to it. So don't worry about any fancy formulas involving midpoints of various things. It's simply think of them as a triangle, and it's pretty obvious from the visually. Okay, so in the second part, they've taken away that value of m and they've made it general again. And they're asking for a value of m for which the line is tangent to the curve. So this requires knowing a bit about the solutions to the formula. So if we write the formula down here, we're going to go x is equal to, so this is if you have the quadratic equation ax squared plus bx plus c is equal to 0, then the formula tells you that x must be equal to minus b plus or minus, because there's two possible values, square root of b squared minus 4ac all over 2a. This can be, you can find derivations. It basically involves completing the square, worth doing once if you haven't, and then forgetting all about it. So this will obviously have this means solutions. Intersection points mean the solutions to this equation, the x values. And once you have the x coordinate of the intersection point, you can find the y coordinate easily. But let's focus on this. So what does it mean if there's if we have a parabola and a straight line? What does it mean for this to have two possible values? Well, it means that this plus or minus must be coming into play. So this thing inside is very important for deciding what kind of intersections we have. If the thing inside is not 0, is positive, let's say it's 4, then one of our values will be plus 4 here, and one will have a minus 4, and so there will be two different ones. So in this case, so maybe I should put this on the side. So case 1, 2. So okay, this is also worth clarifying. Remember that if you take the square root of a negative number, you get an imaginary number, but you don't have to worry about this in pure 1. So let's just be a little careful and just say 2 real solutions. Now, for that to be true, the thing inside this, which is called this discriminant, and often they write it like with a big capital Greek delta. So the first case, 2 solutions, delta is greater than 0, which is the thing that is required for this to like actually have any effect on the equation. This gives you 2 intersections. Well, actually, I should clarify 2 real and different solutions. Gives you 2 intersections. Case 2, 1 solution, 1 real solution, or you can think of it as 2 repeated, same solution. Delta is equal to 0, in which case this thing inside the square root will just be 0, so both of them will be equal to minus b over 2a. This gives you tangent. Why is it tangent? Well, if you think of some general parabola doing this business, if we have case 1, then that's going to cross at 2 different points, right? There,
yeah,
and there. And It only crosses at one point. Well, how can it do that? It can only do that if it just touches it and then goes away. And that's a tangent line. It's tangent at that point. So they're asking us to find a non-zero value of m for which the line is tangent to the curve, and then ask us to find the coordinates of that. Well, for this, you're going to need to use the formula because you don't have a value of m, so you can't do any like easy factorization. So you plug all of that in from the formula, which is now, I should write it down somewhere. The formula has now become x squared minus 4 plus m x plus 4 is equal to 0. So that's the equation that you obtain by setting these two equal to each other. So you just plug them in here where b is minus 4 plus m. Don't forget that minus sign there. A is 1 and c is 4. If you plug all of that in, you'll get two values for x. You'll get 0, and you'll get one which I think is, it doesn't really matter, but minus 8. So they want the non-zero one. The reason they've done this is because they're not interested in one where y is equal to 0. That's just a straight line. That's, well, okay, it's always a straight line, but that's like an uninteresting function. But they're asking for the non-zero value. So if m is equal to minus 8, now you plug that into your formula, wherever m appears, and you will get the x coordinate, and then you plug that into there, and you get the y coordinate, and the problem is solved.
Brilliant. Great. Shall I have a little break? And then do the last couple of questions? Okay. Just sense that you guys are getting a little bit tired. Just like 3 minutes because we'll run over a little bit now. And then we'll wrap up. Nice one. So you see, it does get a bit long to go through. So, and also what you're doing is explain quite a lot to that, which is not a bad thing to do. But of course, you wouldn't be doing it every time. You see, that's the challenge, isn't it? So you've got to sort of explain a little bit about it. And I think it's quite nice.
I do enjoy explaining a little bit because I think that is the route to the insights and the way of thinking.
I like that as well. I especially like the way you were talking about normalizing. And that's quite good. So that's the sort of thing, rather than over a period of time we'll realise that actually the actual doing of it isn't so important. But but this is great and it's good. Okay. So if we can use smaller, and then we can zoom and do it a bit more space to it as well. We'll work it out. I'm thinking that I might have to put some spaces in just a little bit more.
It would be good.
It would be helpful, wouldn't it?
Yeah, just have the margins bumped up.
Yeah.
So I can run something down.
Well, we were thinking of kind of almost having it as a two. I mean, you could do this, and you could have a page layout like that, right?
You know what would be good is the one at the end, because then you could have the question running all the way along and like a blank.
But that's different files.
Yeah.
That's different files, so that doesn't. So I think what we're going to try and do is get one page. Now I'm wondering why that is the same as that. Is that because I didn't see it through?
Maybe we should zoom out.
Possibly, yeah, possibly zoom out. Right. The thing is that you got quite small, but you could insert a page, you see. No, I think here. You could add a page. I could go to here, and I could add a page.
I'm going to skip the next part.
Great.
Another.
Yeah, and do another one.
Yeah.
Yeah, no problem at all. Great. So,
Thank you.
no problem. Sorry. It's probably your brain's probably full anyway, isn't it? Yeah. Okay, close. So you could do it like that, let's see, where you had a.
If you scroll up, maybe. And this is the last area.
I think that's, so I don't know whether that would be better or not. I mean, then you'd The only thing about this is you can draw on one or the other, which is a bit of a pain.
Well, let's keep
we'll see.
going
Yeah,
this
keep going
way.
with this way.
I just think like slightly higher margin, bigger margins, because then you could keep the charm of this
Yeah,
without.
yeah.
Hmm.
Let's go back to this and delete that. Delete that page, back to here. Close. And that's why we'll test and see what people think. Okay. Right, so what would be good, we've got question 10 on the next page. We've really only got, let me show.
Question 10 is.
It's not too bad, is it?
It's not too bad, I just got integration in it, which I
Yeah.
don't know how much that's in. But not sophisticated really. Like just polynomials. So the next question's just a bit.
Yeah, a little bit trickier.
Yeah, I think it's just knowing what range and domain is. And
Yeah. So if you,
Sorry to interrupt. Grace is just playing the piano. Is that going to be
no, it's fine.
an issue?
No, it's fine. I don't think it'll come across. We can ask Albert.
Okay.
You can talk. Albert is watching it. So you could talk to him and ask him whether you can hear the piano in the background.
Okay, that's
But I don't think so. Okay. Right. So we'll try. I mean, again, for first time, if we don't finish the whole paper, it doesn't matter. You know, the very first time we do it. But it's kind of nice to. It's probably better to try and finish the paper with just kind of more insights rather than worry too much about going in depth this time, because I think they probably had a fair amount of depth already.
Yeah.
Okay. Just do the last 15 minutes.
Yeah.
That's a break.
Okay. Do you want mine? I'm fine with that. I really understand.
And also, the point is, this type of approach is, as I say, it is very much in at the deep end. So we're going to kind of whiz through the last 3 questions with showing some insights, and I'll take it from there. Okay, are you back on?
Okay. So question 8. This first bit where they say express this in that form, this is the technique known as completing the square. So this thing cannot be expressed as a perfect square without some extraneous stuff at the edge. You can't just factorize it into a squared bracket. So the procedure involves first removing this, or taking it out of the x terms. So you have 2 times x squared minus 6x plus 13. And then you look at this and you think, okay, what kind of bracket involving a single power of x plus some number, this x plus b thing, what bracket would give me this plus a number, which we'll compensate for? Don't worry about what it is. Well, we want something that where there is simply an x there, which gets squared, and then something that comes out twice. So if I expand this, just this little bracket, I would get x squared plus 2bx plus b squared. So this 2bx is my 6x. So obviously b must be minus 3. So I will find that I can actually express this as 2 times x minus 3 all squared plus 13 as before. But wait, now this thing will also give me this b squared term. So I need to compensate for that. So I need to subtract off whatever will extraneously come out of this. Well, 3 squared minus 3 squared is 9. That then gets multiplied by 2. So I've got an extra 18 coming out of here. So I compensate by minus 18. And that's it.
Yeah.
That is the completing square. It's just taking it from that form to that form. If you do it a couple of times, you won't forget. And that is actually, if you do this with a very general equation, one of these ax squared plus bx plus c, if you do that, you will derive this equation. And that's how it's done. Okay, so now they're taking us back.
Let's just
Yeah. Okay, so they're talking about a function So this is some function of x, which is a one-to-one function. Now, if you look at this, initially, it looks like a parabola because it's got an x squared there. So you'd expect something that's, I think it's something like that, maybe. So this is not a one-to-one function. Anything with x squared is not one-to-one because minus 5 and 5, will have two different values. Because for a given value of y, I have two values of x that will give me that y. Because of the squared, because of the plus or minus sort of ambiguity.
So whenever you see a squared, it can't be a one-to-one function.
Exactly.
Yeah.
But it can't be a one-to-one function globally. But what if I say, no, I don't want the whole of space going off to infinity. I only care about this section. Now it's a one-to-one function. Any given value, if this value of y, it just doesn't pick up that side. You're only talking about what it has on this side. So as long as you restrict what's called the domain of the function, so the domain is the input values for which the function is defined. So if you have this equation and you want a one-to-one function, you're going to have to restrict the domain to be over there, or over here maybe, or maybe just a little section up here, whatever you want. But at the very least, it cannot. If you want these guys, you cannot go over here because now you're curving back up. So that's what the question is asking about. It's the smallest possible value of k. So the leftmost that this limit can go before you start getting the uptick again. So really, it's asking you for the x coordinate of the minimum of the parabola. So there's some equations that you can memorize. For the reason that they've asked you to do this in the first question is they want you to think of this equation. So let's say it's re-expressed as 2x minus 3 squared minus 5. And they want you to realize that when, to compare this to say a normal equation like x squared, let's say y, okay, y is equal to x squared. Well, what is this? This is a parabola centered on 0. But if you add something inside there, inside the squared, you shift the x value of the minimum, of the whole thing really, you shift it along the x-axis by 3. And if you add something over here, like this minus 5, now this shifts the y value by down by 5. You can find that, so if I say have y is equal to x plus a squared plus b, this shifts by the x, shifts x by minus a and y by plus b. So there's a little difference between those two. Now that is, so basically you can know the minimum. The minimum if a and b were not there would just be 0, 0. Your just basic parabola over there. But now we have one that's been shifted across by plus 3 because it was a minus 3 in here, and down by 5. So the x coordinate at this point is 3. And that is the minimum value of k that you would need for this thing to tick up, for the function to be defined as 1 on 1. And that's all the question is asking.
Cool.
Now, there are other techniques for finding out, like the minimum. I think the most reliable one is using derivatives. So if you take the first derivative, if you know it's a parabola, you know there's only one minimum or maximum point, so you don't have to worry about multiple points. You take the first derivative, set that equal to 0, and you solve for x. So that's another very quick way if you're comfortable with calculus. So it needs to be 3 at least for 3 1-to-1. Now they're saying that it's 7, which is allowed. And they're asking us to find the range. So the range is kind of like the partner to the domain. So the range is the possible things that f can output. So here is the domain. F takes it to the range. Okay, so I mean, there might be like a whole space of real numbers, but if I take the numbers in the domain, I can only say reach this section, and that's called the range. So the range of f is all of the values that f of x can spit out if basically if x is greater than 7. So all of these values from the minimum upwards. Well, actually not from the minimum, from when it's from 7, which I guess is there somewhere. So it'll be all of these. So this will be something of the form y is greater than or equal to some number. That's all there is to it. And now they start talking about the inverse function. So this is where it gets a little bit tricky. An inverse function you can solve for pretty straightforwardly. Is you just basically solve for x in this equation. So let's see what that might look like. Let's call it y. F of x, call it y. So we have y is equal to well, actually let's put it inside, very convenient, this formulation we worked out. 2 times x minus 3 all squared minus 5. So x minus 3 is equal to the square root of y plus 5 over 2, plus or minus. So x is equal to that plus 3. So if we were then talking about, they're just being a bit confusing here, f to the minus 1 of x, this is a new function called f to the minus 1. We could call it g if we wanted to, and just say that g is equal to f to the minus 1. It's just the inverse function, and it's a function of x. Whereas this thing we've got here is actually a function of y, by the way we solved it. All they're asking for you is to substitute, is to like switch the labels. So f to the minus 1 of x is going to be something like x plus 5 over 2. We've just relabeled x and y. Now, I've chosen the positive root. As you go through it, it should be plus or minus, but we can actually restrict that because of the values that we worked out for the range in the domain. If we had the negative root, then this thing would be always less than, it would be, the allowed values of x in this equation, they've been very silly and tricky with the x and y, but the allowed values of this x, red x, were the allowed values of y. So that would be the range of f. In fact, it was 27. And that is this red x. This y is actually the red x in this f to minus 1 of x. So x must be greater than 27. If x is greater than 27, this thing is always going to be, 27 plus 5 over 2 or more. It's never going to get any smaller with increasing y, increasing red x. So this thing is always going to be minus the square root of something that's bigger than 0. And so this whole thing, f minus x, is always going to be greater than 3. But f to the minus 1 of x, it's kind of like the x of our original thing, which has to be 3. This thing should just be gone through in like logical detail. They're just being mean. But
and these, I think it's really hard to get this sort of thing. You'll need to do this probably 10 or so times to really get it. I mean, Mark, we've been through this a few times, and it's a bit tricky what they do, isn't it? Yeah. So, but I think that's okay. I think everyone's brain's about full now. Yeah. It's I mean, we'll leave the last couple of questions. It's 2 questions. It's not bad for the first attempt to just about an hour and a half to get through all of that. So that's amazing. So unless you want to do any more, I mean, I think they're about done. Yeah.
It's up to you guys. If you want to have a go at that question, next question on your own, if you've got any time, it's simple, basic, different calculus. And I think there's
The last one was some integration. Isn't it?
the last one's got integration. In fact, no, the question line also has some integration at the end. But they guide you through it. So if you've done any integration at all, we're happy to look at like a simple introductory one. Otherwise, we can go over to the next time.
So the final thing is, this is your Slack team, AS Maths. So Hannah's on that. So what's going to happen is she's available now for tomorrow, or to be on the chat to ask any questions. You know, when we did number 7, you can even say on the PDF where you said this bit, I wasn't quite sure about that step.
Absolutely. So if your questions about what we've done, or if you want to have a go at the next 2 questions and would like some help with that, just let me know, and I'll be able to chat.
Brilliant. Okay, done. Guys, well done. I'm going to stop the video now and stop the broadcast.